Welcome to the course Excelling with Mathematical Modeling. Today is my third lecture on this stability of the dynamical system, and today we will be discussing about Lyapunov stability. Before that, let me recall these quadratic forms. What is quadratic form, what is the positive semi-definite, what is positive definite, negative definite, and so on. So, we will be using this in the definition of Lyapunov stability. So, start with an expression of the form summation I equal to 1 to n, summation j equal to 1 to n, aij xi xj, where your aij's are real numbers. So, an expression of this form is called a real quadratic form. For example, if I write ax square plus 2hxy plus by square, where your a, h and b are real numbers, then this is a quadratic form in two variables. The variables are x and y. Similarly, ax square plus by square plus cz square plus 2fyz plus 2gxz plus 2hxy. This is a quadratic form in three variables. I can put numerics of this ABCs, so I can write say 4x square plus 5xy plus 9y square. This is a quadratic form of two variables. If I denote this by phi, which is equal to I equal to 1 to n, j equal to 1 to n, aij xi xj, then there exists a matrix, a unique symmetric matrix such that phi can be written as some x transpose b x, where b is this unique and symmetric matrix, and we say b to be the matrix of the quadratic form. So, how this is equal to this? Well, we can easily see it with the help of this example. Say, suppose I take this quadratic form 4x square plus 5xy plus 9y square, and I write say b equal to a b h h. If I compare it with this one and this, I will get a as 4, b as 9 and h as 5 by 2, where my x is xy. Generally, it is always customary to write the vector as a column. So, this is my xy and my x transpose will be xy. So, if I now find what is my x transpose xb here, so this will be xy, this will be 4, 5 by 2, 5 by 2, 9, and this is xy. This is 1 cross 2, this is 2 cross 2, and this is 2 cross 1. So, I multiply this and this, number of rows, number of columns are same, and you will get 2 cross 1. So, 4x plus 5 by 2y and 5 by 2x plus 9y. and this is 2 cross 1, this is 1 cross 2, this and this cancels, I mean sorry, the columns are same, so we are multiplying and our product is going to be a number 1 cross 1. So, x times 4x plus 5 by 2y plus y times 5 by 2x plus 9y, and if we simplify this, it is 4x square plus 5 by 2 xy plus 5 by 2 yx plus 9y square, and hence 4x square plus 5xy plus 9y square, and we get this particular quadratic form. So, this and this, they are the same. Now, let us move on to the definition of positive definite. We now write phi equal to x transpose bx, which is equal to summation I equal to 1 to n, summation j equal to 1 to n, aij xi xj. Now, this quadratic form is positive definite if phi is greater than 0 for all x not equal to 0, where this is the null matrix, and it is equal to 0 for x equal to 0. The quadratic form is called positive semi-definite if phi is greater or equal to 0 for all x not equal to 0, and it is equal to 0 for x equal to 0. Number 3, the quadratic form is called negative definite if phi is less than 0 for all x not equal to 0, and it is equal to 0 for x equal to 0. Number 4, this quadratic form is called negative semi-definite if phi is less or equal to 0 for all x not equal to 0, and this is equal to 0 for x equal to 0. And finally, this quadratic form is called indefinite if phi is greater than 0 for some x not equal to 0, and phi is less than 0 for some x not equal to 0. So, with this definition, we now move on. So, with this definition, we now move on. If we take an example, say 5x square plus y square plus 5z square plus 4xy minus 8xz minus 4yz, and we have to check under what category it falls. So, the trick is that you try to make this a whole square. So, if I want to make this a whole square, so instead of taking say root 5 whole square, I will write it as 4x square plus y square plus 4z square. The extra is x square plus z square plus 4xy minus 8xz minus 4yz, and that is equal to 2x whole square plus y square plus 2z whole square plus 2 into x into y. So, 2x into y, which is 4xy, matches with this, minus 2 into x, which is 2x into 2z, again matches with this, minus 2 into y into 2z, matches with this, plus 2 extra terms, which is x square plus z square. So, this can be written as 2x minus y minus 2z whole square. Let us see, 4 minus xy, so this is plus 4xz yz, yeah, plus x square plus y square. So, you can see that this is always positive for all non-zero x, y and z, and this is only equal to 0 when x equal to 0, y equal to 0, z equal to 0. So, which satisfies this definition of positive definite, and hence this quadratic form is positive definite. So, that is how you just prove. Now, let us move to this Lyapunov stability. So, this is another way of checking the stability of the system without explicitly integrating the differential equation. So, the man who is gave this idea is Alexander Mikhailovich Lyapunov, and his concept is that if you have a differential equation dx dt equal to some function of x with an initial condition, then he used a idea that if the potential energy has a relative minimum at the equilibrium point, then the equilibrium point is stable. So, basically if you have a minimum potential energy, then your stability your equilibrium point is stable, otherwise it is unstable. So, let us check that what is this relation between the stability and this potential energy. I mean, how do you relate? How, when potential energy decreases, you get more stability. So, this can be explained by this example which I saw in YouTube, and it goes like this. You consider 2 electrons, say these 2 electrons, and I put them in a vacuum. This is my setup 1. Then after some time, I move it here, and since they are both negative, obviously they will move apart. So, this is my second setup, call this setup 2. Now, I say that setup 2 is more stable than setup 1. Now, how it is that? So, I say this is stable and this is unstable. So, it is like this, that this arrangement 2, it is more preferable by nature than arrangement 1. And why is that? Say you start from an initial condition, say from here, and if you drop a particle, so obviously it will come here, oscillate a bit, and ultimately it will settle here. So, the nature wants that if you drop anything, a particle from here, so it will settle down here. So, in the similar manner, that if you keep these 2 particles as an initial condition, and then after some time I move it here, and I saw that they moved apart, which is obvious because you have 2 negative electrons and they will move apart. So, hence for nature this is more convenient than this one, and hence we say that this system 2 is more stable than system 1. So, unless we have these 2 of them, I cannot compare. So, if only this is there or this is there, then it does not make any sense. So, I have to have a second option or second diagram through which I can compare that which one is more stable than the other. So, in this particular case your setup 2 is more stable than setup 1. So, I say that this one is stable and this one is unstable. Say if I take another, one is positive, another is negative, put them in vacuum. So, this is again the setup 1, and after some time I will see, because one is positive, another is negative, they will attract each other. So, again I say that this is more stable than this one. So, I categorize this as stable and this as unstable. Now, I have moved this from here to here. So, there is some change in energy. So, the question is that what happens to this total energy, and as we know that energy is neither created nor destroyed, it was changes to one form to another form, and because it is inside the vacuum, this holds true. So, moving this from here to here, there is a change in energy and we know that is the kinetic energy. So, I say that let us, here the kinetic energy is 0. So, here the kinetic energy is 0 and here say the kinetic energy is 10. Now, the question is where the initial energy comes here, and that is where the potential energy comes. So, here inside there is some potential energy. So, this configuration already has an inbuilt potential energy, say U equal to say 50, and I moved it from here to here, which use this which generates this kinetic energy of unit 10, and since the total energy remains constant, in this particular case your U will be 40. So, what you notice that from here to here your potential energy decreases and your stability increases. So, from unstable, or rather this setup is more stable than this one. So, as your potential energy decreases, your stability increases. The same thing is here, from here to here I have moved this frame. So, there is a kinetic energy, say that kinetic energy is 15. From moving to here, initially it was 0, here it was 15, U I take that to be again 50. So, here U will be 35. So, again there is a change in the potential energy which decreases from its initial point, from its initial configuration, and you move from unstable to stable, or rather this configuration is more stable than this one. So, with this example it is clear that as your potential energy decreases, you attain more stability. So, this Russian mathematician Alexander Mikhailovich Lyapunov, he generalized this principle and he figured out a method for studying the stability of this autonomous system. So, what is the condition for this Lyapunov stability? So, he says that he defines an autonomous system. So, this is the autonomous system with the initial condition and this is the critical point. Here origin has been taken the critical point. If there is an x star as the critical point, the same thing holds true, or you can shift the origin to x star. So, this system has a critical point x equal to 0 and this function has a continuous partial derivative for all x. Then he defined a function Vx which he called as the Lyapunov function, and this function must be positive definite in the neighborhood of the origin, and the derivative of this function which is v dot x with respect to this system must be negative semi-definite in the neighborhood of x equal to 0. So, if you get such a function, then this V is called this Lyapunov function of the system. If you want to look at mathematically, so this Vx is called a Lyapunov function if your Vx is positive in the neighborhood of the origin, I mean the equilibrium point, in this case it is the origin. V0 has to be equal to 0. Now, V dot has to be negative semi-definite. So, it is less or equal to 0 in the neighborhood of the origin and V dot 0 equal to 0. So, if all these 4 conditions satisfies for a function Vx, we call this a Lyapunov function. So, if there exists a Lyapunov function, if you can find such a function which is not unique again, and there is no hard and fast rule that how you will find that function, but if you can find that function in the neighborhood of the equilibrium point, in this case it is origin, then the steady state solution is called Lyapunov stable. However, if V dot is negative definite, then it is called asymptotically stable. So, we have to just check that whether a Vx exists, then this function has to be positive definite, V0 has to be 0 and the derivative has to be negative semi definite. If it is semi definite, if it is Lyapunov stable, if it is negative definite, it is asymptotically stable. So, this is the result for this Lyapunov stability. Let us check with examples. Before that, so this is Lyapunov condition for global stability. So, whatever we have studied previously, those are local stability. By local stability, I mean that if you have this as your equilibrium point and you start somewhere in the neighborhood of this point, then this is going to reach the equilibrium point is the system is stable. But this global stability, you consider the entire domain, and no matter from where you start in the whole domain, this is going to reach this particular equilibrium point if the system is globally stable about that equilibrium point. So, this is the basic difference between this local stability and the global stability. So, local stability is in the neighborhood and the global stability is in the entire domain. So, for x equal to 0 to be globally asymptotically stable, first it has to be locally asymptotically stable. That is, a Lyapunov function must exist. That function has to be positive definite and the derivative has to be negative definite, not semi definite, because it is locally asymptotically stable. And once you prove that it is locally asymptotically stable, you see that whether this mod of the Lyapunov function, it goes to infinity as the norm goes to infinity, which is known as radially unbounded. If along with locally asymptotically stable, the function is also radially unbounded, then we say that the x equal to 0 is globally asymptotically stable, in short, gas. Now, let us take examples. So, the first example that we take, say dx dt equal to minus x minus y, dy dt is equal to x minus y cube. So, if you want to find the fixed points, so from here, so you put this equal to 0 and this equal to 0, and one of the fixed point is your 0 0, which you can see from here because it can satisfy the equation. So, you find the matrix A, which is minus 1 minus 1 1 minus 3 y square, and at the point 0 0 you get this value as -1, -1, 1 and 0. And if you want to calculate the eigenvalue, which is -1 minus lambda, -1, 1 minus lambda equal to 0. And this is going to give lambda equal to -12 plus minus I root 3 by 2. Well, this is what we have done before, and this is also called Lyapunov's first method. What we learned about this Lyapunov function is called Lyapunov's second method or direct method. So, here we define the function Vxy equal to say ax square plus by square, where a and b, they are positive constants. Well, obvious question is how I choose this function. As I told you, there is no hard and fast rule. After looking into examples, few examples, you will understand. First of all, this function is positive definite, because you can see that other than x equal to 0 and y equal to 0, this function is always positive. So, it is positive definite. So, we just write this is greater than 0 for all x and y not equal to 0, 0. And also V00 is equal to 0. So, very important that you check these two properties. Next comes V dot xy. So, V dot xy is dv dt, which is del v del x into x dot plus del v del y into y dot. Now, del v del x, from here it is 2ax, and this x dot you substitute from here, which is minus x minus y, plus del v del y 2by, and y dot from here, which is x minus y cube. Now, you simplify. So, if you simplify, it is minus 2ax square minus 2axy plus 2byx minus 2by to the power 4. So, I get minus 2ax square minus 2by to the power 4 plus 2xy into b minus a. So, this is my v dot. So, I will choose the a and b in such a manner such that this is less than 0, either less than 0 or less or equal to 0. If it is less or equal to 0, then this will be negative semi definite. If it is only less than 0, then it will be negative definite. So, it is clear that if I choose b is equal to a, and whatever may be the value, if I choose b equal to a equal to either 1, 2, half, whatever the value you choose, this is going to vanish, and you are left with minus 2a x square minus 2b y to the power 4, which is always less than 0 for a equal to b, and say I put 1. So, in this case it is minus 2x square minus 2y to the power 4, and which is always less than 0 for non-zero x and y. So, this becomes negative definite. So, your v is positive definite, your v0 is 0, and your v dot is negative definite, which means that the system is asymptotically stable. So, this is locally stable about the origin, or rather asymptotically stable about the origin. Now, let us see whether your Vxy is radially bounded or not. So, you have to find the norm of x and y, which is square root of x square plus y square, and as x comma y tends to infinity, this also tends to infinity. So, x square plus y square, which is the norm here, this tends to infinity, and at the same time your vxy, which is now x square plus y square, this also tends to infinity. So, you have shown that vxy tends to infinity as this norm tends to infinity, and hence vxy is radially unbounded. So, your condition for global stability is fulfilled, and you say the system is globally asymptotically stable. So, to sum up, what you have to do is you first find the equilibrium point, then you have to write the Lyapunov function. I mean, you have to write the function vxy and show that it is a Lyapunov function. This is totally will come from practice. There is no hard and first rule. By doing few problems, you will understand what kind of function you have to take, and you have to show that this function is a Lyapunov function. That means it has to be positive definite, it has to be 0 at the equilibrium point, in this case it is origin, and the derivative v dot has to be negative definite or negative semi definite. In this case it is negative definite if you choose b equal to a equal to any value. In this case I have chosen 1, and once it is done, you prove that, you show that the system is asymptotically stable. Then you have to show that it is radially unbounded. For that you take the norm, and as xy tends to infinity, this norm also goes to infinity, and this vxy also goes to infinity. So, by the condition of globally asymptotically stable, the Lyapunov's condition, so as your vxy tends to infinity, as your norm goes to infinity, and that condition is fulfilled, and you say the system is globally asymptotically stable. We take another example, say dx dt equal to minus x plus y square and dy dt equal to minus 2y plus 3x square. So, as usual, we define our vxy as ax square plus by square. Clearly, your vxy is greater than 0 for all x, y not equal to 0, 0, and at the point 0, 0 the value is 0. Clearly, here also x equal to 0, y equal to 0 is your steady state solution. Or equilibrium solution, because this satisfies this equation. So, I now find what is my v dot. So, your v dot is del v del x into x dot plus del v del y into y dot 2ax into minus x plus y square plus 2by minus 2y plus 3x square. So, if I open this up, minus 2ax square plus 2axy square minus 4by square plus 6bx square y. Now, so what you do is, here is an x square, here is an x square. So, I take minus 2x square common, and you get a minus 3by. Similarly, from here I take minus 2y square and it is 2b minus ax. So, the reason I choose minus because I have to show this is less or equal to 0. Now, if I want this to be less or equal to 0, so clearly I must have a minus 3b is greater than 0 and 2b minus ax must be greater than 0. So, if these two are positive quantities, clearly then this will be less than 0. So, y. So, the condition becomes a should be greater than 3yb and y should be less than a by 3b. Similarly, 2b minus ax is greater than 0, 2b must be greater than ax and x should be less than 2b by a. So, if I choose again my a equal to b equal to 1, then I get x must be less than 2, y must be less than 1 by 3. So, if this condition holds, then your v dot x y is less than 0 and I can say that v dot is negative definite and hence the system is locally asymptotically stable. But if I choose my a to be say half and b equal to 1 by 4 and if I substitute it here, here and here, I get b is 1 by 4, a is half. I get x is less than 1 and y is less than 2 by 3. So, the condition changes, but you still attain the asymptotic stability. So, this is how your Lyapunov function is being used to calculate the stability of the system. In the next lecture, we will be talking about the phase portrait and the phase plane analysis. Till then, bye bye.